is actually very special, and I'm going to pass this mic to Catherine Gady from NIST, who will tell you exactly why it's very special.
Well, good morning to everyone. It is my great pleasure this morning to have the privilege of introducing the winner of the ICAP 2014 Young Scientist Prize. And this is Jacob M. Taylor. And the ICAP Young Scientist Prize was established in 2007, so this makes Jake the 8th winner of the prize, and thanks to Toshiyuka Azuma, the commission's secretary, we had 32 nominations from 17 different countries, and I think that's it was great fun, and they were excellent. It was highly competitive, and we all want to congratulate Jake. The award consists of 1,000 euros and a medal and an invitation to speak at either the ICAP or the ICPIC meeting. And so this is the award prize ceremony. Jake did his PhD with Misha Lukin at Harvard, a postdoctoral at MIT, before accepting an invitation to become a fellow of the Joint Quantum Institute and a physicist at NIST. That's a position that he now holds concurrently with one as the co-chair of a Joint Center for Quantum Information and Computer Science. Jake has received numerous awards, all starting with graduating from Harvard with a summa cum laude and Phi Beta Kappa. And more recently, he's won the Presidential Early Career Award for Scientists and Engineers. He's won the Service to America Call to Service Award and numerous silver medals. You've got the idea. So this morning, he's going to speak to us on quantum sensing and simulation with light and matter. And Jake, if you would come up, I would like to present you with an ICAP. Certificate.
Thank you, Catherine.
You've been practicing that.
Catherine, thank you so much. And
Congratulations.
it's really a great honor to have this opportunity to talk. The example, by the way, the unofficial criterion for the Young Scientist Prize is the ability to hop on the stage. So it is, however, worth mentioning that receiving this prize is really not something related to me, but it's actually something related to this collection of characters. So this is the research group that I've been working with at the Joint Quantum Institute since I arrived about 5 years ago. And I would say it's through the hard efforts of, some 14 of us, 15 of us working very hard over the last 5 years that we've managed to make some interesting progress and a few problems of interest and relevance to the atomic, molecular, and optical physics communities. So I'd like to think that this award is a reflection of the strong effort and thought that these folks have put in. In particular, I'd like to point out that everyone who's in a circle, I'm going to touch upon some of their work today. And if you didn't get circled, that's okay. You're doing awesome things, but I just ran out of space. And so I also want to point out that several of these folks have a poster this afternoon, and I encourage you to get some more details about what I'm talking about today at their poster. What I'm going to talk about today is a pretty diverse set of topics, and it would be my pleasure to tell you a little bit about them, but also, if the chair doesn't mind, if you have a question as it arises, don't hesitate to raise your hand and ask. Because I find a dialogue is much more meaningful for everyone involved than a monologue. What I'm going to talk about today, in broad strokes, touches upon the role that quantum optics and the story of atomic physics has in building devices that are kind of the emerging technology of the second quantum revolution. And I'll be describing some ways in which we can use our knowledge of quantum mechanics, use our knowledge of atomic physics, and apply it for metrological problems with large mechanical objects, for moving signals between microwave domain and optical domain, for developing architectures, even for quantum computing, using solid-state devices, and for designing new approaches for simulating states of matter that we hope to see but have not been observed in the laboratory, so-called quantum simulation. And I wanted to mention what I think is obvious to me, but nonetheless is worth telling you, which is that photons are a pretty good quantum object. You can control where they go using linear optics. They have extremely good coherence times. If you look at the photons coming out of Junyi's clock, right, it has a coherence length greater than the round trip distance, from here to the sun. And they even work really well at room temperature, because room temperature for a photon is cold. And room temperature is about 7 terahertz, and photons up there to a few hundred terahertz. So you have great opportunities for doing quantum physics at room temperature, terrestrial style domains, if you choose to use photons. They do, however, have a few challenges. And the most notable really dominated the last session yesterday, which is that photons have this pesky problem that they don't interact in the low energy sector of QED. So if you want photons to interact, you have to actually work through matter. Some other problems related to that, one of them is that they don't thermalize because they don't interact. So you have to, when you want to connect your quantum simulator with photons to the thermodynamics and condensed matter theory that we have, you have to realize that you're almost certainly not going to be in a thermal regime. You're going to have to use some new approaches for understanding these systems in order to extract the information that your simulator is trying to tell you. And then finally, unlike most other particles, photons easily disappear because they have no rest mass. And as a consequence, you'll have to do whatever you're going to do in a timescale that is faster than the photonic decay. So with those remarks out of the way, let me tell you the simplest thing that we do with light. And that's to sense acceleration. So here is a sort of cartoon of an acceleration sensor that John Pratt conceived and is now being run by Felipe Guzman Cervantes, sort of a super postdoc at NIST, which corresponds to a test mass here on 2 leaf-style springs. Think of these like the springs in an old-school truck suspension. And this is attached to a large rigid support. So if the rigid support moves, the mass stays behind, and then it starts oscillating back and forth. The key point is that the motion of an object overall is changing the position of this mass relative to the support. Now, if the support holds up one end of an optical cavity, and this is attached to the other end of an optical cavity, this motion changes the length of the cavity. It's an interferometer, of course. Consequently, if you can monitor the resonance frequency, you can detect the position of this object. And this turns out to have a very simple consequence for acceleration sensing, which is that if you get some very good mechanical engineers in the room, as John Pratt and Lee Kumanchek are, you can design a device such that the actual low-frequency response of the system is a simple change in the position as a function of the acceleration. It's a linear response. And this can be made good to actually several orders of magnitude. And the crucial thing thing here that's quite nice about the system is that this cavity length is really a wavelength. And there's two things that we can do really well when it comes to standards. We can do frequency, and we can do length. Of course, they're the same because the speed of light is defined, but you get the basic concept that if I can make my acceleration signal depend just on change in the wavelength of light and the frequency of an oscillator, I can have a direct calibration to the System International, the system of units that we use. And here, all we've really done is taken a sort of MEMS-style electronic accelerometer that I'm certain 98% of the audience has 3 of these in your pocket, inside your cell phones, and made it calibrating by moving to the optical domain. This is not just a hypothetical device, this is the actual device that they built. There's 2 different versions of it, a low frequency one and a high frequency one. It's made out of glass. The color here is just a pseudo color for your eye. It uses a Jakob-Reichel style fiber cavity. There's 2 of them here. Actually, this one here has been donated by Jack Harris's group at Yale. Thank you to Jack for providing that. And this leads to ability to observe acceleration. Here's the acceleration noise in units of little g, acceleration from gravity at terrestrial height, as measured in g per root hertz. And it kind of is not so apparent here, but this is a really beautiful noise curve, which allows you to do acceleration sensing with large bandwidth, with extreme accuracy. And it's actually taking us into a new domain when it comes to what you can measure for acceleration. But it's not quantum. It's just sort of indicating why we got interested in the question of the role that light and mechanics play together. What's going on behind the scenes? Well, here's your system again. You've got an optical cavity, you have a spring and a mirror. And there was a pump laser in that system because you're shining light in to get the interferometric signal out. The length of the cavity sets the resonance wavelength in Fabry-Perot cavity. Change the length, the resonance frequency changes. When I have a frequency change with respect to length, I can recast that in terms of a force. This is the radiation pressure force. What does it correspond to? Essentially, it's the intensity of the field at the mirror, E squared, times position. That's the interaction. You put that large pump in, and then you look at the fluctuations away from the pump, the quantum fluctuations of the system. So I take this electric field, and I put it into a classical term, which is oscillating very rapidly, and then the quantum fluctuation. And if I look at the cross term, I find a coupling between the mechanics and the optics, which is oscillating at the pump frequency. It's a parametric coupling. So it frequency converts up and down between a megahertz for the mechanical motion and 100 terahertz for the optical motion. This, by the way, is the story of optomechanics as it's told today, which is to say, you start with a small nonlinear coupling. I call this nonlinear because it's at least cubic in creation and destruction operators of a bosonic or fermionic field. And nonlinear here also means that my ability to classically simulate this system is gone. But by putting on the large pump field and looking at the first order fluctuations, I recover a linear coupling, which is now large and it's enhanced by this pump strength. This may sound like I'm telling you something new, but in fact, you knew this already. You knew it because you're hearing me speak, and I'm using a microphone. And a microphone is an example of this technique. So here is a typical microphone. I have a membrane capacitor. I put a voltage bias on it. Then if the capacitor moves, right, the change in position changes the capacitance, which causes a fluctuation in the voltage. If I were to turn the power off on my microphone, I take this bias voltage down to 0, and I get very weak coupling. And you can understand that the coupling of the system is proportional to the applied voltage, just as you would expect without the mechanical system. Famously, this led to a novel design for detecting sound, embodied in a great seal of the United States given by the Russians to the US ambassador in the late 1940s. Inside the Great Seal is this little box. If you want to see it, I believe you can actually, it's on display at the Cryptological Museum up on the way towards Baltimore. But the key point here is that this little box was hard to find. It's just a passive little object. What is it? Well, it's a microwave resonator at about 330 megahertz here, with a thin metallic cover that oscillates with the sound, and a large antenna attached to it. And so what they would do is they would beam 330 megahertz radiation at this antenna, and it would reflect back with some sidebands. And the sidebands were the sound fluctuations being imprinted on the light coming back. So you can do it in the microwave domain. You can do it in the optical domain. Why not put them together? As many of you are aware, we have some very interesting quantum circuits working in the microwave domain, superconducting qubits. But also spin waves of atoms. But also mechanical oscillators. And a variety of other interesting signals. For example, astrophysical photons coming from cold sources. All in the microwave domain. But microwave domain requires everything to be cold. So if I want to transfer information from a dilution refrigerator here to a dilution refrigerator at the other end of the room, I would prefer not to do it via a microwave photon. So I might want to transduce that photon up to the optical domain, where I can send it down an optical fiber, where the thermal background, the black body radiation, is essentially negligible at room temperature, and then go back down. So recall the story of optomechanics is apply a pump, and they get a parametric coupling. The pump is basically mixing these two quantum fields, that of the motion here of a mirror sitting in the middle of a cavity, which is a mirror in the middle type setup. We'll talk about that more in a moment. Between the mirror's motion and the optical motion, the optical fluctuations. The story of electromechanics is that story of Theremin's thing, and the story of the microphone and the loudspeaker, which is that the capacitively stored energy is being modulated by this position. No particular reason that I can't put these two oscillators together. So here's an inductor-capacitor circuit, an LC resonator, where the change of the mirror's position here is also changing the capacitance of the system there. And this is now 3 coupled harmonic oscillators, and now quantum opticians delight. We know what to do with 3 coupled oscillators. We can do dark state transfer, we can do dark state polaritons, we can do all sorts of fun physics, because it's 3 oscillators and we know what we're doing. Quantum information theorists maybe are a little bit less excited because quantum information theorists prefer 2x2 matrices, and this is a 3x3 matrix, so one has to be careful. But that being said, the key point here is that you can take an electrical load and transduce it through this resonant circuit through a mechanical object up to light and back. And my collaborators at the Niels Bohr Institute have actually done the first part of this experiment, and then Cindy Riegel has done much better version with the rest of the experiment, and the whole thing now putting together, and she'll be talking about that later this week. I encourage you to hear how you really do it from her. This is our just poor room temperature version of it. But the key point here is that you have a very thin membrane. It's like a drum head made of silicon nitride, sort of introduced the optomechanics community by Jack Harris's group at Yale. And this thin membrane can oscillate back and forth, and it resonates around 1 megahertz. You metallize it. You put a thin layer of aluminum on it. You can also use graphene if you want. It's kind of fun, but we'll come back to that. You metallize it, and you put it above a parallel plate capacitor. Here, the parallel plate capacitor has a pattern on it, so it couples to not the fundamental mode, but the first excited mode. And this is a variable capacitor system. Meanwhile, there's a hole in the middle of this metallization, which lets you send light through the system. So you have all the tools that you need. And as you crank up the voltage, what they found in this experiment was that you can go to a point where the fundamental excitations of the system are not electrical, they're not mechanical, they're combined electromechanical oscillations. They're a polariton. And in this polariton regime, you can actually directly transduce an RF signal up into an optical signal and back. But it's all sort of linear, so it's just impedance matching at the moment. You could ask, can I do this in the quantum domain? And it turns out that this is equivalent to asking the question, can I build a mechanical oscillator whose oscillations can undergo at least a complete coherent cycle before a dephasing event happens. And as you know, the damping rate of a mechanical oscillator is not its dephasing rate. Because when it's hooked up to a thermal bath, it dephases by the addition of phonons as well as the subtraction of phonons. And so what you really want to compare is whether the mechanical frequency, omega, exceeds the damping rate times the thermally enhanced loss process or gain process. And this is recast in another framework, which engineers prefer, which is that you want the Q, frequency over damping, times the frequency of the oscillator to far exceed the thermal frequency. Temperature is expressed as a function of frequency. So you need mechanical oscillators with Q frequency products in excess of 7 terahertz if you want to see room temperature quantum effects in these systems. What's amazing is that now several groups across the world have just passed that threshold. If you're willing to go cryogenic, things are much easier. But even at room temperature now, groups are getting to Q frequency products of 10 terahertz, 15 terahertz, 20 terahertz. Optomechanics is providing room temperature quantum technology. And it's not doing it by using photons at 100 terahertz. It's using it by using mechanical excitations down at a gigahertz or 100 megahertz. So I see a great potential here. We're going to come back, by the way, to this optomechanics story. But I need to take a little detour. And my detour is focusing now on this question: how do I connect up different quantum systems, and why? So where are we with quantum devices? Well, as you've heard and you'll continue to hear, people are building really interesting quantum devices at the few qubit level. Some of them are just incredible in the level of control that you're able to achieve. But these few qubit devices have a bit of a problem, which is that they're all finite size, and when you get to these high fidelity regimes, there isn't really a comprehensive way to couple them up together. So you need a mechanism to take these finite size objects that are sort of fixed in place and couple them up at a distance. My preferred mechanism is to use distributed excitations, photons and phonons. And of course, there's many implementations of this, and again, you'll hear some of it today and some of it tomorrow, Oscar Painter and Cindy Regal and the like. So these beautiful systems over here, you want to couple to these systems over here. How do you do it? Well, as an example case, very typical atomic physics kind of example case, you can start with a semiconductor double quantum dot. So here's a double quantum dot in a theorist picture. It's a double well potential. This one's got 2 fermions in it. You can easily understand it in terms of just a single electron to start. The electron can hop back and forth. With 2 electrons, it's actually a spin excitation that can go back and forth. If you apply voltage across this, it changes the bias between the 2 wells, which causes some tunneling to turn on between the 2 devices. And if there's a spin-orbit term, that tunneling in turn turns to spin rotation. So an applied voltage causes spin rotation. What's an applied voltage? Well, it's an electric field. It's a photon. So Jason Petta's group at Princeton, along with at the same time Andreas Wolfer's group at ETH Zurich, started building devices where you have a superconducting strip-line resonator. It's just a piece of coax, capacitively terminated. That makes a resonator. You put it on a chip, you make it flat, you make it have superconductors, it makes a very good resonator. This resonator had a voltage here, which drops across that little pin. What's sitting inside here is actually a indium arsenide nanowire with these depletion gates underneath it. That allows you to control this double dot system. And then you can do some fun games. Here they were looking at the phase shift through the cavity due to the spin state of this double quantum dot system. Now we're pressing in towards 2 of these. Here's the device from Petta's group, which we'll hopefully hear about in the not too distant future. I won't go into details today, but essentially they're building now superconducting cavities with double dots on either side in order to couple up these dots. Why is it interesting? Well, the length scale of the double dot is 300 nanometers for the whole thing. This circuit here, as you can see, is a few millimeters. So you're bridging a length scale domain. And you're taking, in principle, very good quantum memories and making them operate at good length scales. But these spins are actually not so great because they have a large amount of electrical contact. You like to, if possible, to reduce that electrical part, to reduce the noise. And in fact, some of the best coherence times have been reported, finally beating beryllium. Beryllium is really wonderful, but eventually we got to slightly longer than beryllium for coherence times. And this is done in silicon, where you've got these impurities, single spin impurities attached, where the nuclear spin coherence times in particular can be extremely, extremely long. I think 3 hours is now the best reported value from the group in Canada. But the big challenge with single impurities, which anyone who's worked at NV centers also knows, is that they're basically dipole coupled. And dipole coupling between spins gets very weak very fast. This is not like Rydberg's, where 40 microns later you can still see it. Right? 40 nanometers later you can barely see it. So we need some technique to couple these things up. So I'm going to tell you technically about some ideas that Michael Gollins, my postdoc, has been developing in order to get good entanglement between these systems using the atomic physics techniques that we know and love. Purcell enhancement, and superradiance. So you need to take just a brief moment into a picture of what one of these impurities looks like. It binds an electronic state, here as basically a single electron state, to the system. It has a Cramer's doublet ground state, that's the spin. It has some mid-infrared states up here, the 2s2p and the 1s states. And then it has bound exciton states up here, where you actually create an electron-hole pair which attaches to this thing and it's below the band energy. So when you look at these beautiful coherence time experiments, they do them by optically polarizing the sample. The optical polarization mechanism uses this bound exciton transition. So this is a spin controllable. The spin polarization rules are quite good. You can also, in principle, make a pi transition down to these mid-infrared states. This is not so great for doing quantum optics because these things are strongly coupled to phonons. And the consequence is that the decay pathways here are actually not photon decay, they're phonon decay. I emit lattice excitations of the system. And in particular, the terahertz domain phonons dominate. So our key idea here was to essentially change this by modifying the decay channels. And how do you get rid of this phonon decay? Well, you make another decay channel even stronger. Now, terahertz is interesting because in terahertz, we actually have some good candidate excitations. They're called plasmons. Plasmons are very localized electromagnetic excitations on the surface of metal. And in graphene, they actually work really nicely in the sense that they have an extremely small group velocity compared to the speed of light. So they compress everything to a very small length scale. And as you know from cavity QED, volume matters. So for Purcell enhancement, very, very small volumes associated with plasmons lead to very strong decay. So what we've been thinking about was a strip of graphene sitting above two of these impurities. And what you find, what's really amazing, is that this very strong enhancement leads to a 10 to the 7-fold enhancement of this terahertz photon decay mechanism. And so you go from having no photon decay at all to having photon decay that's 10 or 100 times stronger than the phonon decay. And these plasmons in graphene actually have a very long coherence length. Graphene, it kind of is a wonder material, only at cryogenic temperatures. And what that allows you to do is essentially get a plasmon decay channel which is coherently talking between two different impurities. The two different decay processes can interfere with each other because the plasmons are coherent over the length of the distance between the two objects. That's what we call superradiance or subradiance. The destructive interference is subradiance. The constructive interference is superradiance. Already back in 1999, this was suggested as a mechanism for making entanglement. Martin Plenio and co-authors. More recently, Anders Sorensen's group showed a very nice way of doing this in generic settings. And the key point is that you take this system, you drive a transition which can now decay, and you do so in a spin-independent way. You mix all the triplet states, and it leaves behind, after optical pumping, just the subradiant state, the singlet state of the system. That's the only thing that doesn't decay. And so it's just an optical pumping mechanism, here actually done in the terahertz domain. There's also really nice implications for this story because this allows you, in principle, to make terahertz detectors and terahertz sources, because you can actually detect the plasmons in the graphene after they've decohered because they correspond to electronic excitation. So you can do electronic readout of these systems. I'm now going to sort of move from spin coupling to looking at going back to just using the light as much as we can. And I mentioned before, one of the things I like about light is you can control where it goes. If you want to say it in a slightly less prosaic language, you can engineer the meaning of excitations in a photonic or phononic system. And we know this kind of intuitively from the tight binding model. Just take a crystal, where each atom's like a harmonic oscillator. And the point is, when I move an atom, it produces a force on the nearby guys. And so I get these collective oscillations of the system. We can call these collective oscillations phonons. And has some dispersion relation. But the dispersion is actually determined by the structure of the lattice. And by controlling the structure of the lattice, you can control the meaning of excitations. In the continuum limit, these are sound waves. But more generally, by controlling the propagation properties, you control what the excitations are, what they look like. There's many examples of this now in terms of photons and phonons. Think of these photonic crystal devices and the like. This has been primarily focused on bandgap engineering. More recently, as you saw on Monday's talk by Mahmoud Hafezi, you can actually get to the sort of quantum Hall domain with light, where he was showing the ability to manipulate the band structure of these systems and actually get topological edge states of the system, shown here. And if you want to hear more about that by Sunil, Mittal has a poster this afternoon describing some recent advances we've been doing there. So you can see that working with light, it's very easy to control what the excitations look like. Now, as atomic physicists, the analogy you should think about, of course, is that of optical lattices. But a crucial difference here is that we're aiming for room temperature technology, chip-based technology. And if we can get that, I think we have a really interesting opportunity. So let me now describe a way to take the optomechanical system and find a chip-compatible single photon nonlinearity that can operate at room temperature. So as I mentioned before, when I had that electromechanical system and it's strongly coupled, the excitations are no longer mechanical or electrical, but they're electromechanical. They're polaritons. Well, let's explore that polariton regime. What's happening? I started with a nonlinear interaction with some quantum coupling G0, the number occupation in the cavity, and then the position, B plus B dagger, of the oscillator. I put a high power in. This system looks like a linear coupling between two positions. Generically, when I linearly couple two harmonic oscillators, everything's groovy. Here's an example of two coupled oscillators, one at frequency of about a half the other. I start increasing the coupling, and this one starts going up, this one starts going down, and everything's fine, everything's fine, everything. Oh, wait a second. The system goes unstable if you pump it too hard. What happens as you approach instability? This is a very special point over here, because the potential of the system, the sort of X potential of the polariton, is changing as you push towards here. The spring constant is weakening. So you start here with a tight spring and a tightly confined wave function, then it spreads out and spreads out some more the closer you get, and the wave function keeps getting broader and broader and broader. The position fluctuations are being enhanced as you get to the instability. And this coupling here, this underlying nonlinear coupling, depends upon the position. So we realized that you could use this, first of all, to make very good squeezing. Not the first people to realize it, but we're the first people, I guess, to put it in a particular framework where it actually is understood to be very good squeezing. But also you can use it to make a nonlinearity. Now I need to add a slight technical improvement. We need to move to mirror in the middle. And the mirror in the middle is essentially, I just want to add an additional optical mode, so I have a symmetric and antisymmetric combination. There's a high reflectivity mirror sitting in the middle. This original coupling that we had before was an A dagger A, now becomes an A dagger B plus B dagger A. Basically, you flip from symmetric to antisymmetric by changing the phase, which is the motion of this mirror away from its equilibrium spot. And near the instability, this coupling becomes kind of peculiar. It looks like this. in the polariton phases. And you can get nonlinearity. I'm actually kind of short on time, so I won't tell you too much about it. But the key point is that you have a figure for the quantum nonlinearity, which is this ratio of g squared over kappa squared. Kappa is the optical decay. Everyone's trying to get g over kappa greater than 1. The best is about 0.05. But now you have this other factor here. This is what we call sideband resolution. And so if you can achieve this, and you can get a Q frequency product that's about the same as P, Q frequency compared to kappa that's about the same as P, then you can, in fact, achieve a room temperature quantum nonlinearity for the system. You can kind of see some performance just shown here. This is the G2 of this system as you increase this P parameter, and it gets to be pretty good, though. You need to get to pretty high Ps before you get there. It's worth mentioning, you should see the poster by my student Hai-Tan Zhu and Utku Kumarchik, postdoc, who has been looking at high reflectivity gratings in John Lawal's lab. So here's a picture of a membrane in the middle system. This is a low reflective piece of dielectric. As you move the membrane, you get these sinusoidal cavity modes. What they were able to do was make a high reflectivity grating by etching through the silicon. This is, again, a thin layer of silicon nitride. And what happens is light comes down, it diffracts off this pattern, the pattern diffracts back, and shoots back up. And that makes this high reflectivity picture here. You zoom in, you get this only 50 megahertz splitting now. You sort of get into the high reflectivity regime. You can hear more in Hai-Tan's poster. And in the remaining few minutes, I'm just going to mention where we're kind of going now, which is towards quantum simulation in a more immediate time scale, because all that wonderful optomechanics requires a lot more engineering than where we've gotten to. We kind of have glimmerings that it's going to be possible, but there's a huge research program yet to be enacted. But there is, however, an alternative approach. You know, when you want something, you go look at the obvious place, as this piece of Americana suggests. Of course, I'm certain if we asked Mr. Sutton about nonlinearity, he would have said something along these lines, which is, of course, we should look in the microwave domain, because that's where the nonlinearity is. What is the nonlinearity? Well, of course, there's also this Rydberg story, which is very interesting, but you heard all about that yesterday, so I won't go into the details. What's really nice about the microwaves are simply that you get a good conductivity in superconducting devices, which allows you to make cavity modes with a center line conductor. That means that your transverse confinement of your cavity mode can be much smaller than wavelength squared. So your mode volume can now be orders of magnitude smaller, and that brings the coupling way up. The other thing is that you have the Josephson junction, which is a very nonlinear object. And the two things together combine, it's nonlinear in the sense that the cosine potential has this 5/4 term in it. The two things together combine to produce a huge wealth of new opportunities. So as an example case, this is more of a technical slide, just consider what's called a fluxonium qubit. So it's an LC circuit. Here's the capacitive energy, here's the inductive energy, and there's a Josephson junction. Simple Hamiltonian. Look at the potential, apply a flux through the system, some biasing flux. What do you get? Well, you get a potential in the phi space, which looks a bit like this. It looks like a harmonic oscillator. You can see these dashed lines. But then there's this other well over here. And what's interesting about this is that this is harmonic, harmonic, harmonic. Now this suddenly looks harmonic, but it can tunnel. So it's a dramatic change of the harmonic nature of the system. And that leads to an effective description, which is like a resonator with some 2-photon nonlinearity, and now a strong 3-photon nonlinearity. And you can continue this process to go to 4 and 5 and 6. This is very different than what we expect physically. Usually we expect that when I want to go to multi-body interaction beyond two-body, I have to work extremely hard. But the superconducting state provides a new opportunity. So you kind of go into the details of it, and you basically find that there's a regime where you can get this U2 parameter to be 0, the U3 parameter to be on the order of a tenth of the Josephson energy. So it's a very strong effect. Okay. The other last missing piece, in addition to making interesting nonlinear interactions, is setting up the state of the system. Now, I mentioned before, photons don't thermalize. More famously, photons don't have a chemical potential. Now, you hear it from Martin Weiss's group, also I think later, maybe it's tomorrow, about making BEC with light. I'm just going to tell you that the problem is simply simply put that the natural state for a photonic system is the vacuum, because if you look at the system and system bath and the bath interaction, I find in thermodynamic limit that I go to a system which is thermalized. And this, by the way, in gory detail is worked out in this PRE. I know it seems obvious, but there's some subtleties. So the next point is to bring the bath to the system. So if you take the same coupling, but you change the inner bath coupling to oscillate in time, you make a parametric bath coupling. This situation changes. You go to a rotating frame. There's a certain regime in which you can make a rotating wave approximation. I get a new picture. The system bath coupling, and the bath, and now the system is modified because I'm in this rotating frame. This thermalizes to this state, which you notice has a chemical potential. And what's going on is you have a parametric bath down here at low frequencies that's being up and down converted to the system. There's also a photonic loss channel, but that's the fundamental idea. Now there's a way to implement this using superconducting circuits, using this Wheatstone bridge construction. There's a way to do it optically using optomechanics. I don't really have the time to talk about it, but if you want more details, we have it up in our preprint. And this beautiful device is described in this Nature paper. And if you want a sort of example of how this applies, consider a very favorite system, right? The Bose-Hubbard model, where each of the sites has an on-site interaction, and there's tunneling. All very simple. Now we're going to add is a little parametric bath at each site. This calculation was a little bit laborious. This is the many-level spectrum for just the 2x2 plaquette. And you can see that there's the ground state, the gap. Here are the hole excitations. Here are the particle excitations. And basically, the probability of being down here is pretty high because I can exchange energy with the thermodynamic bath, and I can both create particle and hole relaxation by this parametric coupling. If you look at the actual phase diagram, here's a 2x2, a 2x3. We can go to higher now. The key point is that you get these Mott lobes, and if you look at the particle hole picture, everything looks fine, except there's something a bit funny, which is that the system has a decay process through photons and the high-frequency domain, which makes it highly asymmetric with respect to particles and holes. And so as you go to high photonic decay, so a third of the parametric bath decay, you get that the particle hole lobes are moving up a bit. Okay. So I'm really out of time. I just want to leave you with this image from Andrew Hauck's group, where they built an array of 116 superconducting resonators. And I would say that there's no technological limit now for taking all these fun ideas you can generate and building quantum simulators out of them and really designing the Hamiltonian in any way you'd like. For that, I'll just conclude by mentioning that we have a new effort starting at University of Maryland and at NIST, which is called the Joint Center for Quantum Information and Computer Science, where we're actually looking to take some of these sort of higher level concepts and explore them in great detail. We have to ask, what are we trying to learn about physics and chemistry and biology by building quantum devices? We want to ask, what does the nature of computation tell us about physics? What does the nature of physics tell us about computation? We also want to ask, how do we actually work in a world in which people have quantum devices, in which the second quantum technology revolution has taken off? How do you do e-commerce? How do you do your measurements? How do you build your computers? How do you build the infrastructure around it? So these are the questions that we're going to look into. We have a visitor program and workshops and the like. Please drop me a line if you want some more details. And I'll just conclude by mentioning again that what I've told you today is really the hard work of these people. And it's really upon their backs and with their great effort that we've had all these successes. Thank you for your time.
Thank you, Jake, for the wonderful talk. We have time for a few questions.
So Jake, it's Bill over here. Surprise, surprise. So I came in a few moments late, so I apologize if you already addressed this, but all this wonderful mechanical systems, MEMS and optomechanics, which have quantum sensitivity, is there any chance that these kinds of devices could contribute to the scandalous, to the resolution of the scandalous situation with Big G, where, you know, obviously we're looking for really, anyway, you know, could you, well.
Sure, I'd be happy to address that question. So as you may be aware, we're working with quantum devices which could be massive. And so you can ask, can I start to measure mass-related things better? One of the famous examples is Newton's gravitational constant, big G, which has some interesting discrepancies in recent experiment. So very briefly, just like in the accelerometer project, where we're really not in the quantum domain, there's nothing special about the quantum domain for big G measurement. When what we've been looking into is actually a somewhat different question, which is, can I learn anything else about gravity in those same experiments? Can I learn something about, for example, does gravity convey quantum information? When I measure big G, what else am I learning? And so we actually find that it might be possible to design experiments not just to measure big G, but at the same time to constrain the set of theories of gravity which some people have posited may exist and that don't actually allow gravity to communicate quantum information. But I would say that there's nothing particularly special that optomechanics has brought to that. What's much more important is the advances in material science that are enabling these really high Q-frequency products. Because at the end of the day, it's the actual material imperfections which are a big issue when you build those experiments. But you should talk to Stefan Schlaminger, who's at NIST and is now in charge of the kilogram, if you want to get the great details on that.
More questions?
In the back and...
I would just be, it's hot. I'd just be curious to hear a little bit more about how you couple the plasmons on graphene to quantum dots, and how exactly are they coupled to each other?
Well, what maybe wasn't so clear is that the graphene story is not for quantum dots. It's actually for single impurities. But the story is basically the same. You can couple to the graphene simply because the graphene has plasmon excitations. Right? These are essentially tightly confined electromagnetic excitations. They have, because they're electromagnetic, they have some distance outside of the graphene that they extend. And that distance scales on the order of the width of the strip in this case. So it's some 30 nanometers, and so it's just a near field coupling effect. But you have to be quite close.
Thank you. More questions?
When you couple the cavity to the capacitor, why would the moving mirror actually change the voltage across the capacitor?
So if I have a capacitor,
Yep.
and I've applied a large voltage across it, if I suddenly move one of the plates.
Well, but the mirror was like in between of them.
Oh, no, you think it's actually, it's two capacitors in parallel. So there's, you just have to use my hands for a moment. I have one capacitor like this, and this is then hooked up to another capacitor like this. And this is the same top plate and two bottom plates.
I see.
So that's actually how it works.
All right, I think we're out of time, so let's thank Jake again.